Hello, everyone. See that some people have already started joining. I decided to kind of open up the webinar a little early here. So if you wanted to put in the chat box, maybe a little background about yourself, if you're a farmer, if you're in the Delaware River watershed, perhaps, if you're in Pennsylvania or New Jersey, feel free to just type something in the chat box and kind of get to know who I'm talking to today. Hopefully everyone's able to handle the heat that we've been having out here. If you're experiencing this crazy heat wave we've been having in Pennsylvania, I know our farm ops team and all of our technicians are drinking plenty of water and eating a lot of popsicles right now just because it's so hot. Oh, great. We have someone from Tennessee. Nice. Going to get started in probably a minute or two just to let more people come in. I know it's always hard to kind of get to these things on time with how technology is. Oklahoma, awesome. Welcome, David. Hi, Amory from Sinking Spring, Pennsylvania. I don't know what part of Pennsylvania that's from, but I imagine you're kind of going through the same crazy weather we're going through right now. Let a few more people come in here. Maryland, welcome. Ah, Tim from State College. I did my PhD at Penn State, so I'm envious that you guys have cicadas there right now. I guess it's good for a webinar not to have the cicadas in the background, but I actually had to travel about an hour south to go find them. More Pennsylvania, more cicadas, awesome. Okay, I think I can get started. There's a little bit of housekeeping at the beginning too, so people that are gonna pop in a bit late won't miss any of the fun science. So welcome, I'm Dr. Kirsten Pearsons, and I'm a postdoctoral researcher here at the Rodale Institute, and I'm working primarily on the Watershed Impact Trial, which is what I'm going to be updating you guys on today. This project is actually a collaboration with the Stroud Water Research Center, and they're really focused on kind of the water side of things. We're here at Rodale, we're really focused on the soil health and more agronomy side of things. This project has been funded by the William Penn Foundation, and their overall goal is to protect the Delaware River and the Delaware River watershed. And that's why they're funding projects like this one to get an idea of how we can change management practices to improve the quality of the Delaware River. If you have any questions, please put them in the question and answer box. I'm probably not going to have time to revisit the chat box, but feel free if you have kind of any discussion to go ahead and use that chat box. But if you have a specific question for me to answer at the end of the webinar, put it in that Q&A. If you're having any problems, any connection issues, or you're having a hard time finding that Q&A box, feel free to give a call to Maria Pope. She's our education coordinator, and she's the one who's kind of helping run this. So to jump right in, this is a picture of the Delaware River. As you can see here, there's a lot of human impact in the Delaware River. There's actually a dam crossing the river in this photo, but there's also a lot of things you can't see. There's runoff from agricultural areas and urban areas and suburban areas, and there's various different human activities that can affect this Delaware River. The Watershed Impact Trial specifically is a project where we're trying to compare organic and conventional agricultural systems to determine their relative impact on the environment, especially water quality in the Delaware River watershed. Our goal overall is to change the management practices that growers are using in this watershed specifically, and hopefully some of these practices through this study will be adopted elsewhere beyond the Delaware River watershed. So some of these conservation practices that we're looking at include the reduction or elimination of pesticides, like organic farming, the planting of cover crops. So these are plants that are grown in crop fields, but not while the focal crop like corn or soybeans is growing, and helps to provide cover for the soil and living plant material that can really help protect soil and conserve soil. And then also reducing tillage. So tillage or plowing is the breaking up of soil or turning over, loosening of soil to help manage weeds and to prepare the seed bed for planting. But it's really destructive to the soil, and it can increase things like soil erosion. And so by reducing tillage, you can help, again, protect that soil. And as I've mentioned soil a few times, obviously you can see that a lot of these practices are indeed adopted to improve soil health. Soil health is defined as the continued capacity of soil to function as a vital living ecosystem that sustains plants, animals, and humans. So there's been a concept of soil quality around for quite some time, which is really focusing on kind of the chemical composition and the physical characteristics of soil. But soil health really brings into the idea that soil is that living ecosystem, and there's this important biological component that these conservation practices can support to overall improve the health of plants, animals, and humans. And one aspect of soil health is really focused on water quality, so looking at how healthy soil can change the quantity and quality of water that's running off of these agricultural fields. So that's what we're really focused on in this project. Zooming out a little bit so you can get an idea of the scale of the Delaware River watershed. It's primarily the Delaware River with a lot of tributaries that are in Pennsylvania and New Jersey. For some context, if you're not from this area, this is where Philadelphia is. It's actually really close to the Delaware River. The Rodale Institute is up here in Allentown, so still part of that darker area, which is the Delaware River watershed. And our collaborators at the Stroud Water Research Center are a little bit closer to Philadelphia on a different tributary into the Delaware River watershed. The Delaware River watershed is actually quite large. It's 13,000 or so square miles, and about 10% of this land is dedicated to agriculture. So while not a lot of this watershed is specifically agriculture, it can have a quite kind of greater impact than a lot of other land uses. Something also to really consider is that 5% of the United States drinking water comes from the Delaware River watershed. So it's really important that we protect this single watershed specifically because it does contribute to a lot of the drinking water. And if the quality of this water isn't great, that's going to have huge economic and health impacts. So one of the projects that is part of this bigger project is actually our long-term farming systems trial here at the Rodale Institute. It was originally established in 1981. This is just an overhead picture. You can see that there's a variety of different crops grown in these really long plots in this system. We have three primary different treatments or management systems. One of those is the manure organic system, which is all organic practices with a diverse crop rotation. And we use animal manure as our source of fertility. So this is where we're getting our nitrogen, our phosphorus, and various other nutrients. And we decided to use manure because this is a pretty common resource, especially in a dairy cropping or a dairy production area like here. Often there's a lot of manure kind of sitting around, and it's a great source of nutrients. In addition to the manure system, we also have a legume organic system, and this was designed to be a really low input system where it's all under organic management, but there's actually no fertility input to the system. So all of the nitrogen is actually coming into the system through legumes, which can pull nitrogen from the atmosphere and bring it into the soil for plants to take up. So legumes are things like beans and peas, and what we're using primarily are vetch and clover cover crops. And of course, to compare these organic systems to kind of the standard practices that most growers are using, we have a conventional system which uses synthetic pesticides, synthetic fertilizers, and genetically modified crops. In 2008, after recognizing that a lot of growers were changing their tillage practices, we overlapped another treatment onto these systems, and that was a different tillage treatment. So before 2008, all of these systems were always tilled before planting crops or cover crops. And so that's what this top photo is here. And you can see that tillage If you're turning that soil over, you're really breaking up a lot of soil. There's bare soil, and that could lead to a lot of potential for things like erosion. To reduce tillage, there are a few options. In conventional systems, growers will usually just spray herbicides, so they can actually go fully no-till, so not tilling for decades. But then in the organic systems, we still need to till occasionally to manage weeds, but things like corn and soybeans can be planted under a reduced tillage practice where you use something like the roller crimper shown in this photo to roll down cover crops to help manage weeds, and then you're not disturbing the soil as you plant the soybeans and corn that follow. There are some limitations to this farming systems trial, though, when it comes to looking at water quality. We don't have any distinct watersheds, so if there's something going on in the conventional system, that's going to affect the water quality that's coming off the entire field, so we can't really tease apart what's going on in the organic systems. It's also a relatively flat field, so looking at things like erosion doesn't really make too much sense. And they're really, really small plots, so there's a lot of variability across the field that may mask some of the effects on water quality. So this is where our partnership with the Stroud Water Research Center really came in handy, because they have access to some research fields out at the Stroud Preserve down in Westchester, Pennsylvania, relatively close to Philadelphia. And so this is what those fields look like, and you may be able to see that they look a little bit different from the farming systems trial. We actually only have two primary fields, where we have a conventional field, which is split into a no-till and a till treatment. And then we have an organic field, which is split also into a full till and then a reduced till treatment. Something really special about these fields is that they actually have isolated watersheds. So the organic field, all of the water drains into a single stream at the bottom, and none of the water from the conventional field actually ends up in that stream. So we can really look at how organic practices are improving that water quality over time. These fields are also on a relatively steep hill slope, so we can look at things like erosion. And then these larger plots are more representative of what a grower's field will look like, so we can get a better idea of how there's a lot of variability across these fields and how these different practices kind of under different situations can improve soil health and water quality. I will note that we are still working on this project. This is a research update, not a kind of final report. So I'm only going to be able to share some preliminary data today. The project started in 2018, and that's actually when that organic field at the Stroud Preserve first went into organic production. So that field was in conventional beforehand. So we're hoping we're going to see improvements over time, whereas in the farming systems trial, we probably already have some relatively established differences. So if you really want to get the full story, the peer-reviewed story, you got to come back in 2023 or 2024. So what have we been measuring? Quite a lot of things. With soil health, we've been looking at compaction and aggregate stability as measures of physical characteristics of the soil. We've been looking at soil pH and nutrient contents as chemical measures, and soil carbon, organic matter, soil respiration, and the microbial community as measures of that kind of biological activity of the soil. For water quality, we're looking at infiltration through the soil, so how water moves through the soil. We're measuring the quality and quantity of water runoff from these fields, and we're also looking at water contamination from nutrients, so nitrogen and phosphorus, pesticides, and bacteria like E. coli. Of course, we're also interested in productivity, because it doesn't matter if you are cleaning up the environment. If a grower can't make enough money, they're not going to be able to adopt those practices. So we're looking at yield and profitability, as well as energy use and greenhouse gas emissions. As this is a collaboration, Rodale is kind of taking some of the measurements, and Stroud is taking some of the other measurements. So shown here in green are what Rodale is primarily responsible for, and shown here in blue is what Stroud is really helping us out with. Today, I'm not going to be talking about everything for the sake of time, and also based on the kind of data that we do have so far. So I'm going to talk about compaction and aggregate stability, soil carbon, organic matter, and soil respiration as measures of soil health. And I'm going to talk a little bit about infiltration and water contamination, and then highlight yield at the very end. So jumping right into some of these measures of soil health, compaction is really a tool to see how deep plant roots can go. So if a soil is really, really compacted, it's going to be hard for plants to send their roots downward, and that's going to limit their ability to absorb nutrients and water, and it's also going to cause a problem with water moving through the soil. So this picture over here, kind of schematic, I have a plant showing you a plant to show you the roots going down, and that brown line is perhaps a compaction layer. And this is a really deep compaction layer, and so it's not a problem for the plant. The plant can put its roots down far enough. However, with a really shallow compaction layer, roots are not going to be able to go down as far, and you're going to have a sad plant and potentially some other problems. So this layer at which roots cannot penetrate is measured in pressure. So at 300 pounds per square inch, that's kind of the cutoff for most plants. Their roots cannot go through that layer. So these are some data here showing you that the further down you go there, that's a lower depth, so a deeper layer to that compaction level. So it's a better situation in that case. And these are the conventional, organic, and manure plots. I'm going to use the same colors throughout here with conventional shown in blue, the legume organic system, that is the system with no fertilizer inputs shown in green, and then the manure system shown here kind of in an orangish red. And so in the conventional system, the depth to that 300 psi level is shallower. So that does mean that there's kind of a better compaction rating in the organic systems. And then with that introduction of the reduced tillage system, there wasn't an effect in the organic systems, which is great. However, reducing tillage in the conventional system further led to higher compaction or a shallower compaction in those systems, which is problematic because as you are introducing crops into the system, they're maybe going to suffer a little bit because they're not going to be able to reach nutrients or water at deeper levels. Out at the Stroud Preserve, things are a little bit different. So actually I'm presenting the data a little bit differently as well. Instead of looking at compaction as just a straight measurement, I'm looking at a change in compaction over time here. So if the value is above that 0% level, that means that the compaction depth has gotten deeper, so things are improving. And if there's a bar like this blue one here that's below that 0% line, it means that the compaction layer is actually getting shallower, which is not a great thing. So in the tilled systems, the conventional, as I just mentioned, compaction is actually getting a bit worse. Whereas in the organic system, remembering that it was in conventional production until about 2018, things have been improving, which is great. With the reduced tilled systems, things are still improving in the organic system. And unlike in the farming systems trial, things are also getting better in the reduced till or no-till conventional system. Something that is different between these two projects is that at the Stroud Preserve, we're actually planting cover crops in all of our no-till plots. So it's possible that cover crops are helping to kind of loosen the soil and bring carbon into the soil, which can help improve compaction. So if a grower is reducing tillage or is even just using conventional practices, incorporating a cover crop can really help them kind of look more like an organic system when it comes to compaction. The other measure of physical characteristics for soil health that we looked at was the stability of soil aggregates. So a soil aggregate is basically a soil clump or clod or crumb. It's kind of a chunk of soil. And if it is stable, like shown under this good picture here, if it's in water, it's not going to fall apart and it's not going to erode very quickly. So you're going to be able to retain nutrients and soil during like a large storm event. However, if the aggregate stability is really low, that clod is going to fall apart and it's going to release nutrients and sediment in the water during a storm event, and you're going to lose a lot of nutrients and kind of soil quality during large storm events. So in the organic systems, like with compaction, there's not really an interesting story going on. Aggregate stability is kind of just doing its thing. But in the conventional system, there is actually a difference between the no-till and the tilled system, where the stability of these aggregates is actually higher, at least at the surface of the soil in the reduced till or no-till systems. I will note that in the organic systems, it's hard to reduce tillage that much. You can't do full no-till. So if we can kind of move more towards full no-till, perhaps limiting tillage at a few more planting events, we may be able to further increase aggregate stability. At the Stroud Preserve, things are a little bit different than the farming systems trial, where aggregate stability is kind of just generally lower in the organic system. And I'm going to foreshadow a little bit here. This looks very similar to our soil carbon content, where the organic systems, which again have only been under organic production for about 3 years, the soil carbon is lower just kind of innately based on where it is located compared to the conventional plots. So hopefully over time, under organic practices, soil carbon will increase, and then aggregate stability will also increase. So I just mentioned soil carbon. This is somewhat synonymous with soil organic matter because soil organic matter is mostly carbon. And this is a relatively small fraction of soil overall, but it's a really strong predictor of soil health. So I just have this pie chart here to show you kind of the composition of a standard soil. Most soil is a mineral component, so that's your sand, silt, or clay. And about half of the soil is actually just pore space. So this is empty space. Well, not really empty space. It's space that's filled with either air or water, depending on how wet the soil is. And then only that little tiny sliver there, about 5% on average, is organic matter. But that 5% can really change soil compaction. So it can decrease soil compaction if there's more soil organic matter. More soil organic matter will also increase aggregate stability, as I just kind of hinted at. It can increase nutrient availability and the exchange of nutrients for plants. It can regulate soil moisture. It can increase biological activity. And obviously, as organic matter is mostly carbon, the more organic matter in your system, the more carbon that is sequestered in that soil. So it's a really small piece of the soil, but it plays a really big role. So this is something that's actually been tracked in the farming systems trial since the very, very first year. And overall, kind of what you would expect is that under these organic management systems, soil organic matter has been increasing over time. So from 1981, when the project started, you can really see that the soil organic matter increased in both the manure organic and legume organic systems, but kind of just hovered around the same level in the conventional system. After 2008, there were some changes that were made to the kind of systems overall, in addition to the reduction of tillage in half of the plots. And with the changes, there's a change in rotation in the manure system. So there's a longer rotation and manure wasn't applied as frequently. So things have kind of plateaued in terms of soil organic matter just because the amount of inputs hasn't been as high. And then the conventional system, interestingly, soil organic matter has risen over time. And that's largely because of the no-till system and the occasional incorporation of cover crops in the conventional system. So as we've adopted more conservation practices in the conventional system, soil organic matter is starting to look a little bit more like those organic systems. At the Stroud Preserve, as I already kind of mentioned, the conventional plots at the start of this experiment had higher soil carbon. And that's still kind of the way things were at the end of 2020. So soil carbon can take a really long time to change. You need a lot of carbon inputs, and microbes have to take those carbon inputs and pull them into the soil. So hopefully by the end of this experiment, we will start to see an increase in soil carbon in the organic systems, and perhaps where we're growing cover crops in those conventional systems. So another way to measure kind of the biological activity of the soil is to look at soil respiration. So really how alive the soil is. So just like you and me, microbes actually breathe out carbon dioxide, and that's something that scientists can measure from the soil to get an idea of how many microbes there are and how active they are in the soil. And if there's more active microbes, you're going to have higher soil health. So we measured respiration rates, shown here on the y-axis, and then we measured this at 2 different depths. a kind of surface soil layer from 0 to 10 centimeters, and then from 10 to 20 centimeters a little bit deeper down. And so tillage didn't actually have an effect on this, at least it hasn't in the last few years, but the systems did have a really big effect on soil respiration rate. So shown here from 0 to 10 centimeters, respiration was higher in the manure system, likely because these microbes have access to a lot of really easy to consume carbon sources from the manure and from cover crops and crop biomass. Whereas they don't have quite as much resources in the conventional and the organic legume system. And then from 10 to 20 centimeters, so a little deeper down, the respiration rate is about the same in both of the organic systems, the legume and the manure ones shown there in green and orange, but it drops off a lot in the conventional system. The respiration rate is much lower just beneath that first surface layer of soil. So this means that if a carbon input is put into these systems, the carbon in the microbial activity isn't really going deeper down into the soil. And that's really how carbon can get sequestered. Carbon needs to move down into deeper layers of the soil, and that doesn't seem to be happening as much in the conventional system. Out of the Stroud Preserve, this figure may look somewhat similar to the other figures I've shown for the Stroud Preserve. It really seems that respiration rate is driven a lot by soil carbon levels. And hopefully in the next few years, as the soil carbon levels start to rise, we'll start to see changes in respiration rate. So now, as this is a talk about water quality, I'm going to stop talking about soil health quite as much and move on to some of the measures of water quality. So one thing we measure in the field, infiltration rate, which is really a way to determine if water will move over the soil or through the soil during a storm event. So I'm just going to kind of walk through a little schematic here. Say that there's a really heavy rainstorm and you are a conventional farmer. You have relatively compacted soil. You didn't plant a cover crop. And so you're going to have a huge storm event pushing a lot of water on the soil surface. And it's moving pretty quick because there's nothing there to slow it down. So very little water will actually get into the soil and will move down into the soil into groundwater. So what that looks like is perhaps some water is infiltrating, moving through that soil, but most of it's going to end up as surface runoff or is going to puddle or pool in the fields. Maybe you're an organic grower that has healthier soils, it's less compacted, and you're planting cover crops during kind of the non-crop season. So if you have a large storm event, those cover crops are going to slow down the movement of water on the soil surface because they basically just get in the way. And that's going to give more time for water to move down through the soil. And also with lower compaction and kind of more loose soil and more pore space, the water is more readily going to move through the soil anyway. So what that's going to look like is you're going to have much higher infiltration rates, more water is moving into the soil, and there's going to end up being less surface runoff or less intense surface runoff. And what this means is you're going to have more consistent water availability. Groundwater is more likely to get recharged, and water is also slowed down and filtered before it reaches surface water. So if you have a large storm event and there's a lot of runoff, that's going to lead to a lot of erosion and it's going to cause problems for stormwater management systems. Whereas if there is less surface runoff and more water infiltrating, it's going to be easier to manage that water. So we measure infiltration actually right in the field using these things called double ring infiltrometers. And it's not necessarily the most exciting science because you basically sit there and you watch water move through the soil. But by timing that and knowing how much water we put into the system, we can get really accurate measurements of how quickly water would move through that soil during a storm event. And so these are some of the data here. Like compaction, this is kind of a flipped graph where the longer the columns here, the faster the infiltration rate, which is kind of what we're looking for. And this is actually kind of the opposite of what we would expect long-term here, where the tilled systems shown kind of those darker columns actually have higher infiltration rates than the no-till or reduced systems shown in those lighter bars. Often no-till or reducing tillage is thought to improve infiltration because you're not disturbing the soil system. So things like aggregate stability and soil carbon can rise, which can influence infiltration rate. However, there's something interesting that I noticed while looking through the data. That's just showing the significance of that difference, is that the tilled plots, some of them or most of them were planted in the fall with a cover crop, specifically rye. And that means they were tilled in the fall, and we measured infiltration early in the spring before planting any cash crops like corn or soybeans. However, there were some conventional plots that are normally under tilled management, but because they didn't have a cover crop planted, the last time they were tilled was last spring in 2020. And these plots that didn't have a cover crop but were normally tilled actually had infiltration rates that looked a bit more like the plots that were generally under reduced tillage and had cover crops, but didn't have tillage to plant those cover crops. So it's possible that infiltration rate, at least in this instance, was more reflective of the most recent tillage activity. And this is why we're measuring things like this multiple times a year and multiple times throughout this experiment, because it's possible that certain times of the year, tillage may actually improve infiltration, but throughout the majority of the year, reducing tillage may actually lead to higher infiltration rates, say in summer or in the fall. Something else that we're looking at in regards to water quality, of course, is water contamination. And here I'm just going to talk mostly about nitrates, which is a form of nitrogen. But both nitrogen and phosphorus from various fertilizers can be a huge issue for water contamination. With conventional synthetic fertilizers, this is thought to be less of an issue because growers should be able to really accurately get soil tests and figure out how much nitrogen or phosphorus their crop is going to need and apply just that amount. It can be a little bit harder to do this with something like manure, which has more variable nitrogen and phosphorus content. And also, and so as you can see with the spreader here, it can be a lot harder to get kind of an accurate application rate across the field. So with things like manure, even though they're great for building soil health because of all that carbon that they're contributing to the microbial community, over application or poor application can pose a huge risk to groundwater because of all that extra nitrogen and phosphorus that if plants don't take it up, it's just going to either leach through the ground or leave through surface runoff. So to measure nitrogen and phosphorus, there are a variety of ways and places that can kind of get measured. And we're focusing on pore water. So if you remember that pie chart of soil, how about half of it was organic matter and the mineral component, and the other half was just kind of this pore space, which is either filled with air or water. It's that water that we're looking at specifically because if there's excess nitrogen and phosphorus there, that is kind of an indicator that nitrogen and phosphorus is available to run off in surface water or infiltrate down into groundwater. So the tool we use is something called a suction cup lysimeter, and it's basically a porous substance that we put into the ground, and we put it under vacuum pressure to just suck that pore water in during a storm event, and then we're able to collect that in bottles and analyze it for nitrogen, phosphorus, pesticides, really anything that we're interested at looking at. So I'm just going to talk about nitrates, a specific form of nitrogen. And before I do, I want to remind you that plant roots in our systems are limited at around 20 to 30 centimeters. That's where we're hitting that 300 PSI compaction layer. And so that means that any nitrates or other nutrients that are kind of above that level, there's a good chance that it's going to be plant available and it's going to get taken up by plants before it can be kind of washed away. However, any nitrates or other nutrients that are below that level, it's unlikely that they're going to be taken up by plants, and really the only place that they can go is into groundwater. So this plot here, I'm showing depth, kind of again, it's kind of a weirdly reversed graph where depth gets deeper as you go down, and nitrate concentration here on the x-axis. So above that compaction layer where plants can really access those nutrients, nitrate levels are relatively low and are quite similar across these three different systems. So this is great. It probably means that the plants are actively pulling up those nitrates. However, beneath that rooting zone, nitrates are significantly higher in the conventional system, both at around 30 centimeters and below 40 centimeters. And so, while this is not a full measurement of the total nitrates in the system, having a higher concentration of nitrates in this pore water means that the conventional system may actually pose a greater groundwater contamination risk when it comes to nitrate nutrients. This is kind of the opposite of what we would expect when manure is kind of blamed often for contributing extra nitrogen and phosphorus. And I also want to point out that the conventional system, of course, is also going to have pesticides, which is, of course, a surface water and groundwater contamination issue. So even not considering the pesticides, the conventional system looks to be more of a risk when it comes to contamination. So overall, what have we kind of learned so far from these organic and reduced tillage systems? Well, when it comes to soil health, it looks like organic systems can reduce compaction, and reducing tillage can have kind of a variable effect on compaction. Aggregate stability is higher where tillage is reduced, at least in conventional systems. And soil carbon levels are improved both under organic management and when tillage is reduced, which I think is really critical because all of these other measures of soil health are really tied to soil carbon and soil organic matter. And then under organic systems, soil respiration is higher, whereas reducing tillage doesn't seem to have an effect, at least kind of a few years after reducing tillage. With water quality, we're still trying to figure out what's going on with infiltration in these systems. So stay tuned. Hopefully we'll have more data in the future. And for water contamination, at least with nitrates, it seems like there's lower potential for nitrate contamination in those organic systems. But of course, as I mentioned when I first started this talk, healthy soils and clean water won't feed we need. The easy answer is no, not really, as long as you're using good management practices in your organic system or good no-till management practices. These systems can perform just as well as a full-till conventional system. So this plot here is how I'm actually going to be presenting the yield data. As we're growing a variety of different crops and weather can vary from year to year, which can really affect yield, I decided to compare the yields out at FST to county averages for each specific grain crop. And I'm going to have these stacked bars, and where the bars are hatched, that's the kind of percentage of years at which that system had the same yield or equivalent yield as the county, kind of the county average. And then if the bar is solid, that's actually where our yields were actually higher in the farming systems trial compared to the county averages here in Berks County, Pennsylvania. So as you would kind of expect, conventional systems have been designed to produce, kind of maximum yields. So in most years, more than 50%, about 70 to 80% of years, the grain yields from these conventional systems are either equal to or higher than county averages. So we can farm, and we can farm conventionally pretty well, but how about our organic systems? How well are they performing? Well, the manure system, the system under organic management, where we're applying manure as that nutrient source, actually performs just as well as those conventional systems. At least it's not statistically different. And while it looks like there's a greater chance that yields will be equal to county averages, and maybe they won't exceed county averages quite as much, it's still better than kind of luck that more than 50% of the time we're going to have equal or greater yields, which is great because there is that organic premium. So as long as the input costs, so as long as that manure is cheap, as long as labor isn't much more, a grower adopting these organic practices with manure as a fertility source, they're probably actually going to see higher profits than had they been managing under a conventional system. In the legume system, unfortunately, the yields are a bit lower. There's actually only 1 year where the grain yield exceeded the county averages, and less than half the time we were seeing yields that were equal to county averages. But this is a really low input system where you're not even applying manure. There's no fertilizers that are getting added to this system. So with that organic premium and those lower input costs, even this lower yielding organic system can be more profitable than the conventional system. And this is something that we've actually seen with some economic analysis in FST from years back before this reduced tillage treatment was introduced. And so we're working on actually an economic analysis right now to try to see if reducing tillage can kind of further improve kind of that profit, because you have potentially lower fuel and lower labor when you aren't kind of going through with that tillage event. At the Stroud Preserve, things maybe aren't quite as interesting as the farming systems trial. And the yield there really tracks with soil carbon. So this figure is maybe a little more easy to understand, that it's just looking at the relative yield of the various grain crops in these different systems. So that dashed line at 1 is just that point at which the yield would be equivalent to the county average, in this case, Chester County. In the conventional system, the full-till conventional system actually was equivalent to county averages, which kind of makes sense. It actually saw higher yields in the no-till system. Every single year, the no-till conventional system actually performed better than county averages. Whereas in the organic system, we're seeing lower yields in the full-till organic system. And this doesn't look great, but it tracks really closely again with that soil carbon. So we expect to build more soil carbon in those organic systems and perhaps in that no-till conventional system. So probably by 2023, we're going to start seeing some differences in yield thanks to that new soil carbon that's been added to the system. So to kind of summarize everything here, by adopting these various conservation practices, eliminating pesticides and using organic farming practices, planting cover crops, and reducing tillage, we're probably going to see improvements in soil health. So through this study so far, we've been seeing lower compaction, higher aggregate stability, more soil carbon, and higher biological activity, which has the potential to improve water quality. We're really not quite sure what's going on with infiltration rates quite yet, but we are definitely seeing lower water contamination. And hopefully, as we continue to collect and analyze data over the next few years, we're going to see kind of an even fuller story when it comes to all of these data. And also, based on some of the studies that have been done in the farming systems trial before, there's going to be less energy use, lower greenhouse gas emissions, and potentially greater profitability when these conservation farming practices are adopted. So it seems kind of like a win-win-win that by adopting these practices, the grower is going to make more money, soil health is going to be improved, water quality is going to be improved, and there's some potentially other beneficial externalities just by adopting these practices. Before we go, I do want to mention we have kind of an outreach component to this research project. And if you want to learn more about that, you can go to the growcleanwater.org website, where you can learn more about soil health, the practices that we're doing to improve soil health, and how it affects water quality. There's actually a pledge that you can take as well, just so you can take part in this effort to improve the water quality of the Delaware River watershed. So thank you all for tuning in. I'm going to get to the questions in just a second here. I just want to mention that we have another webinar coming up on June 28th. And this is actually going to be hosted by Dr. Yichao Rui, who is the Farming Systems Trial Director. And he's going to be talking about regenerative agriculture, so a lot of these conservation-based practices, and how it relates to the soil microbial carbon pump, which has to do with carbon sequestration and improving the amount of carbon in soil. Okay, time to answer some questions here. How much land in the watershed is privately owned? I am not quite sure about that. I'm guessing that there's a fair amount of that land is forested and is potentially state-owned. But that is something that could be challenging, is that on state-owned land or on land owned by, say, like universities, it can often be easier to kind of force these practices to be adopted. whereas otherwise we have to work with individual landowners or farmers to try to get them to adopt these practices. At the beginning of the watershed trial, were the measurement outcomes the same between the two fields? In other words, were they equivalent at the start of the study? Hopefully I answered this throughout the presentation, that at least out at Stroud Preserve, these measurements were not equivalent between the conventional field and the organic field, which is why a lot of the time I was looking at changes over time. And it does make it kind of hard to interpret some of the results, but hopefully we can still detect, improvement in the organic system by looking at a change over time and maybe not seeing those changes as much or even declines in soil health in the conventional system. Since everything at the Stroud Preserve seems to track soil organic matter, have you looked into possibly testing for differences, controlling for variation in organic carbon, or possibly testing for interactions between terms, a nested model? I haven't actually built any nested models yet or tried to include soil organic matter in any models. I'm currently working on a paper focused on the last 12 or so years of the farming systems trial data related to soil health. And once I'm done with that, then I'm going to move on to looking more at some of the data that we have from the Stroud Preserve. So I'll definitely keep that in mind. I think that's going to actually be a great way to kind of account for the effect that soil organic matter is having on the various different endpoints, soil health and yields. Have you calculated an input yield ratio for each system? I have not yet. We will be, as I mentioned, running an economic analysis for the farming systems trial. Again, looking at those 12 years from 2008 till now, where the reduced tillage system has been introduced. So might have to be a little bit patient while we're working on compiling all those data, but hopefully we'll be able to show that the input to yield ratio will be lower in the organic system, and then the input to profit ratio will be even lower. What are the differences in labor or effort among the systems? So I do know from previous studies published from the farming systems trial that labor does tend to be greater in the organic system. And this is partly due to the ease of just going out and spraying an herbicide that requires one person, whereas if you're going to be managing weeds with a variety of cultivation, that's going to be multiple passes, multiple people have to go out on a tractor to manage weeds. The previous work has shown too that while there is more labor in the organic system, it tends to be more evenly spread throughout the year. So if someone is hiring someone to work on their farm, they're more likely to be able to guarantee long-term employment, whereas in the conventional system, a lot of the field activities are concentrated just around planting and harvest, and there's less going on during the rest of the year. So even if you're paying less for labor, that labor force is not going to be as stable over time. Is there permanent measure equipment in the fields? Yes, there is. One of the things that we're working with in the farming systems trial are these things called passive lysimeters. So like the suction cup lysimeters I briefly talked about, they're measuring the water that's in the soil at that moment. And these passive lysimeters are basically gigantic drums that are buried under the soil just below the plow depth. So I think it's about 30 to 40 centimeters deep. They were buried in 1990, so before I was born, and they're still working. They're still collecting water. So each year we go out 3 times and we pump out the water from those there's barrels and there's kind of an auxiliary jug of water. We pump out that water and we measure it. And so we can look at kind of a more long-term understanding of how much water is moving through the soil. And we can analyze those water samples for nutrients and for pesticides. And then throughout most of the year, we also have water sensors that are installed in all of the fields. We have to take them out when we're doing things like plowing or planting because we would destroy them. But we are hoping to get an idea of kind of how consistent water availability is across these different systems. And to best do that is to have these water sensors in there for as much of the year as possible. Is there a way to break out cover cropping as an independent variable? In some of our systems, there are. So in the farming systems trial, there are some years where cover crops were planted just in the no-till systems for the conventional plots. But then in the kind of in later years, we actually split up the conventional system where some of the conventional plots are under full till with cover crops, full till without cover crops, and then no till with cover crops and no till without cover crops. So there's some instances where we can split out cover crops as an independent variable, but like out at the Stroud Preserve, where all of our conventional no-till plots have cover crops, we can't actually kind of tease that apart. This is why these are considered systems trials, because we're really looking at, if a grower is adopting these practices, how is that different than this practice? And if we were to try to have all of the different possible combinations of those, we would have far too many plots, and it would just be impossible to actually collect all of the data to kind of figure out what's going on. So it's a compromise you have to make with these field experiments of, looking at a systems approach and getting, enough data to actually find these differences, or really looking at a bunch of independent different changes to the system, but perhaps having, no or very little replication. Do you think more studies like this will encourage more pressure on the policy level for large-scale producers to take on more conservation practices? I think as long as we can show that these conservation practices are actually going to improve their bottom line, that they're going to, have either equivalent or higher yields with lower inputs and greater profit, I think that's going to be the real incentive for a lot of these large-scale producers. I do know in certain regions of the United States, including Pennsylvania, a lot of conventional growers have switched over to no-till or reduced tillage because that's fewer tractor passes, that's less fuel, that's less labor that they have to put in, and they're still seeing the same yield. So it's kind of a no-does situation in that case. And so sometimes it's just a matter of getting, a handful of these large-scale producers to switch over, and then their competitors are going to realize like that's something I should be doing too. I think to put pressure on the policy level, we do need these kinds of studies, but also we need more public awareness. So that's one of the reasons why this project has kind of that outreach component, talking about the Grow Clean Water project, because when more people know about what's going on and know that these conservation practices are an option, we're gonna be able to start a public discourse and hopefully get people excited and interested and kind of putting that pressure on growers, and maybe creating incentives either at the state or federal level for growers to adopt some of these practices. Is the use of pesticides and herbicides increased with moving from conventional tillage to a no-till system where the cash crops are corn, soy, alfalfa, and rye? So it depends. A lot of the time, conventional growers that are, say, growing, I'm more familiar with just a corn soybean rotation, they would apply herbicides soon after planting, which would be called a pre-emergent. So before whatever was just planted actually emerges out of the soil. And then a post-emergent, so a few weeks later to kind of knock down any weeds. And then potentially, if weeds are really bad, still early in the season, they're going to go in again a few more times with herbicides. In a no-till system, a lot of the time, there's still kind of two primary herbicide passes. One pass before planting to kill weeds or to burn down a cover crop. And then another pass a bit later in the season, kind of coinciding with that post-emergent in the tilled system. So it's possible that herbicide use isn't changing that much. In no-till, like in full no-till, if a farmer has not driven through a field with a plow for decades, there often are some kind of changes in the weed community and which weeds are harder to manage. So it's actually something we're seeing out in the farming systems trial, that our no-till conventional system has these perennial weeds that are coming in and are, they almost look like trees because they've escaped control with kind of the standard herbicide regimen that we're using, and we're not able to destroy them with tillage because these are full no-till systems. So in that case, sometimes the herbicide kind of chemicals that are used have to change, and growers just need to think a little bit differently about how and when they're applying their herbicides. When it comes to other pesticides, To be honest, most conventional growers are using seed coatings. So regardless if they're till or no till, if they're planting cover crops or not, they're probably applying an insecticide and or fungicide at planting. And this is actually quite concerning because, if a grower is trying to kind of do their best within a conventional system, so they're reducing tillage, they're planting cover crops, they have a diverse crop rotation, they still may be using these seed coatings that have toxic insecticides and fungicides that then go on to have a negative impact on soil health and the soil invertebrate community. Yet they may not actually need them because these other conservation practices may be kind of helping to manage pests. So it really does come down to kind of what the grower is doing in general. I think that adopting more conservation practices can allow growers to reduce their pesticide and herbicide use. And there's also no reason why a conventional grower couldn't use something like a roller crimper, which we use to terminate cover crops in the organic systems. They could use that instead of using an herbicide to burn down their cover crop, which would definitely decrease their herbicide use. Okay, if anyone has any more questions, feel free to kind of add those into the question and answer box right now. Okay, I'm not seeing any more questions. If you do have any questions that pop into your head, I often find after I watch a talk or a webinar, it's about like an hour afterwards, I'm like, oh, I have a great question that's related to that project. Feel free to email me. My email is here on this slide, and it's also available on the website. It's just my first and last name with a period between the two at rodaleinstitute.org. So thank you everyone so much for tuning in. I hope you learned a lot about the Watershed Impact Trial, and I hope you're excited to see the results that we get over the next few years.